In this video, we'll discuss the three famous problems from the ancient Greek mathematics. Now, one of the most famous paintings in the Vatican is at St. Paul's Cathedral, which is called the School of Athens, painted by Raphael. In this painting, we see many Greek philosophers that have been very influential on society. We have Socrates in the upper left-hand corner. We have Plato and Aristotle. Plato being important because after studying under Socrates, he creates the academy, which then helps to create many of the philosophers and mathematicians that we think of this time, including Aristotle. We also have Pythagoras and Hypatia, Hypatia being considered the first female mathematician of the Greeks. And then in the bottom right, we have who's often considered Euclid, sometimes considered Archimedes, but most commonly Euclid. Now, we think about this time period from 600 to 300 BCE and how monumental it was in improving the mathematics. And it was because the philosophy expected high rigor in mathematics to help enhance how they understood their philosophies. So we have reasoning and logic being used both in mathematics and in philosophy, and they go hand in hand in improving one another, all the way starting with Thales to Euclid creating the elements in 300 BCE. Now, with that came three broad mathematical developments. First, the geometric reasoning and proof led to the construction of Euclid's Elements, which is full of geometric proofs in two dimensions and in the sphere. That also led in this time period to the construction of limits and summations and infinitesimals, and much of that work was the foundation that was not developed fully until calculus was developed later in the Common Era with Newton and Leibniz. Additionally, because of how much work they did with geometry, they started to recognize other types of surfaces where geometry occurs, such as curves beyond circles and spheres, and how that changes some of those foundational definitions we think of in planar geometry. Now, much of the work that was done at that time was used what are called the Euclidean tools. With Euclidean tools, you have a straight edge and a collapsible compass. With the straight edge, there are no markings, so there are no measurements that can be constructed by actually marking the straight edge. This only generates an undefined line, and that is important for what we're about to talk about. The collapsible compass is one that there are also no markings on it, and when you pick it up, it collapses on itself, unlike the modern compasses that we use now. It also will create a defined circle, though. So when we think about the three famous problems, we have to remember again that we're restricted to an unmarked straight edge and a collapsible compass. And because of those two key components, there were certain things that could not be done. One of those was the duplication of a cube. This means trying to construct a cube that has twice the volume of a given cube. The second one is called trisection. Here we're trying to trisect any angle, and honestly they were trying to multisect any angle, but they started with trisection. And the third one was called the quadrature of a circle. With the quadrature, you're trying to construct a square that will have the same area as a given circle. With all of these, the whole key component is that it had to be done with these Euclidean tools. There are mechanical methods to solve each of these, but not with Euclidean tools, and that was not finally proven until the 19th century. So think about it. Thousands of years passed with people trying to work on these problems with Euclidean tools to see if they could be proven to be done. So the first one, the duplication of the cube. Tradition says that what happened was the Oracle of Delos said that the people needed to construct an altar twice its size for Apollos to help end a pandemic that was occurring throughout Greece. The poet incorrectly suggested that if you double each side, then the cube volume would be doubled as well, which we know is not true. Hippocrates then came up with a reduction using two mean proportionals that provided some understanding of this issue and where we have problems with using the Euclidean tools. Now let's see why Euclidean tools cannot help with the duplication of a cube. First, we know that one volume is double the other. So we could write x cubed equals 2 times y cubed. And we use x cubed and y cubed because it's a cube. Therefore, all three sides are the same length. Now, if we take the cube root of each volume, that should give us the length of each side in its ratio. And the problem is that when you do that, you get x equals y times the cube root of 2. And it's that cube root of 2 that's the problem. Because of that cube root of 2, one cannot construct it using Euclidean tools. So the duplication of the cube was never going to be feasible. Now, with the trisection of an angle, it was recognized that you could multisect a segment. They also knew how to bisect any angle, and they could trisect a right angle. So they were trying to see, can we trisect any angle and then multisect any angle? Now, many different methods were created that allowed for the trisection of an angle, just not with those classical Euclidean tools. Pappus and Hippias were able to use curves and conics, but they had to use mechanical means, which means they're marking pieces as they go along. Archimedes used the insertion principle, again, using markings to be able to make this trisection occur. And it helped lead, though, to many different discoveries. So even though these three problems were not possible with the classical Euclidean tools, they did lead to many mathematical discoveries. For example, Nicomedes was able to construct the conchoid, and Archimedes was able to construct the Archimedean spiral. Now, the reason trisection cannot occur is that you have to use a cube root of a conic equation, or you have to use the insertion principle. Both of those will end up violating the ability to use the Euclidean tools. Now, let's think about Archimedes' insertion principle for trisection. The way this worked is you would construct a right triangle BCA. Next, what you would do is create a perpendicular line, and we'll call it line D, through point A. What we would then do is use the insertion principle to construct a segment we're going to call EF, and it had to be double the length of that hypotenuse. Also, we're going to put a midpoint of G on there. So EG and GF also equal the measure of AB. Now, what we're going to do is we're going to align EF on side AC so that if we drew a line through B, F would be on point O, be on line D, and then they would also be able to connect AG to be the same length as EF, GF, and AB. When you do that, what that constructs is this tiny little angle CBE. By that construction using the insertion principle, it will be 1/3 of what would have been CBA. Now, the quadrature of a circle meant to create a square with the same area as a given circle. They could perform the quadrature of a rectangle, so there's the idea of we can do rectangles, why not be able to do other polygons such as and other shapes like a circle? Now, this problem was examined in 1800s BCE by the Egyptians as well, so it was a problem known by more than one civilization. One of the things you got to pay attention to is the idea that the Greeks often considered pi to be a rational constant. And there's the key that causes much of the issue, the rational piece. Now, we think about the area of a circle. It's pi r squared. If we want the area of the quadrature of that circle, so the area of a square with the same area, that will be pi r squared as well. Well, think about how do we make the area of a square? It's the base squared. It's the same value. So if we want to know the length of one side, we would take the square root of our area. The problem is, though, you have pi. And not only pi, you have the square root of pi, and that cannot be constructed using Euclidean tools. Thus, we can't complete the quadrature of a circle. Now, just like the trisection led to different discoveries, there were discoveries by trying to determine the quadrature of a circle, such as the lunes of Hippocrates. Now, the lune was the first quadrature of a curvilinear object, so that makes it even more unique. Now, what is a lune? Let's construct it to show you. So first, we're going to start with a circle, and we're going to construct an isosceles right triangle in the center of the circle. Now, what we do then is create a semicircle off the hypotenuse. The lune then will be all of the part of that semicircle that's on the outside of the original circle. And what you notice here by doing this is that the area of that right triangle inside the circle will have the same area as that of the lune, which allows us then to solve problems and understand the lunes better. For example, if I knew that the radius of the circle is 4 inches, and I would say, well, what's the area of the lune? Since the radius is 4 inches, I know the two legs of my right triangle are also 4 inches. And then I know that the area of the lune equals the area of the triangle. So area of triangle is relatively simple, especially because it's a right triangle. It's 1/2 the leg times the leg. And here that would be the same value. So 1/2 of 16 inches squared will give me 8 square inches. Now the hunt for pi went through many different civilizations, starting as early as the Egyptians and Babylonians. And you see that with the Egyptians and their 22/7 value for pi, they at least got the first 2 decimal places. Archimedes made the next major advancement with the understanding of pi by using perimeters of inscribed and circumscribed polygons to create a boundary. And within that boundary, he actually has the irrational value of pi. He just couldn't say exactly what it was. Hundreds of years later, the ancient Chinese advanced these values with Zhang Heng, who said that pi was approximately the square root of 10. It's a little bit more than what Archimedes found, but that led to other contemporaries of the ancient Chinese mathematics, such as Zhu Shangxi, to compute it to be about 3.1415929. And right there, that's the first 6 digits of pi in 470 CE, not with computers like we use today, but with many other mathematical advancements that they were doing, all with paper, pencil, and their minds. Now, through time after that, you have pi going to 16 places, then 35 places, and 100 places by 1700 CE. And eventually, in 1767 CE, Johann Lambert proved that pi is an irrational number, and that's why we use the symbol today.